There's antimony, arsenic, aluminum, selenium, and hydrogen and oxygen and nitrogen and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, and protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromide, lithium, beryllium, and barium. Isn't that interesting?
3, 2,
I hope you're all paying
1,
attention.
fire.
There's going to be a short quiz later on.
Okay.
There's holmium and helium and hafnium and erbium and phosphorus and francium and fluorine and terbium and manganese and mercury and molybdenum and magnesium, dysprosium and scandium and cerium and cesium and lead, praseodymium and platinum, plutonium, palladium, promethium, potassium, polonium and tantalum, technetium, titanium, tellurium and cadmium and calcium and chromium and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, krypton, neon, radenzine, and zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard. And there may be many others, but they haven't been discovered.
Hello, I want to show an example of a reaction between methanol, CH3OH, and oxygen, O2, which produces carbon dioxide, CO2, and water. It's an easy reaction to balance, although you do have to put a 2 in front of the CH3OH to get it to balance without using fractions. And I'm going to show that this reaction can be explosive. Now I'm going to put 2 drops of liquid methanol into this film canister, and I'm going to cap it. I'm going to put some ear protection on. I'll heat it up for a few seconds, and then I'm going to aim it away from myself. And 3, 2, 1, fire. Okay, so you got to be careful doing this demonstration. But I'd like to discuss the energetics of the reaction. I'd like to discuss why it gives off so much energy. All right, so let's kind of picture what's going on by considering 2 methanol molecules reacting with 3 oxygen to produce 2 carbon dioxide and 4 water molecules. To account for the energetics, let's imagine that we could take the 5 molecules here and break the atoms, break the bonds apart into individual atoms. Now, if we actually count the double bonds as 2 bonds, the total number of bonds broken would be 5, 10, 12, 14, 16. All right, so we break them apart, and breaking a bond requires energy. And then let's take these atoms and reassemble them in the form of the product. So now we're going to make bonds. We're going to make 4 carbon oxygen double bonds to form the 2 carbon dioxide molecules, and 8 hydrogen oxygen bonds to form the 4 water molecules. All right, we're going to look at the bonds broken. We break 6 CH bonds, and they're not real strong, 413 kilojoules per mole. Multiply that by 6, you get 2478. We've got the 2 OH bonds, 467, and the total is 934. 2 CO bonds, 358, and double that, it's 716. And as I said before, the oxygen-oxygen double bond, not that strong for a double bond, and there's 3 of them. And so that gives you 1494. Add it together, and we get, to break all the bonds of the reactants in the gas phase, requires 5,622 kilojoules per the stoichiometric amount. 2 moles of this and 3 moles of that. It requires that much energy to break those bonds. Now we're going to form the bonds, and we're forming 4 carbon oxygen double bonds, which are 799, almost 800, and that's a 3196 kilojoules for those 4 moles of bonds. And for the OH bonds, strong single bond, 467 times 8. So we add it together and we get 6932. So it requires 5622 to break the bonds, but you get back 6932. So if we take how much it requires to break the bonds minus how much you get back, you get negative 1,310. The negative simply means that energy is released. 1,310 and 10 kilojoules of energy are released.